Hello guys, welcome to Smart. In this video we are going to show that the intersection of two topology is also a topology. Now before we show that this intersection of two topology is a topology, let's first of all do a quick review on intersection of sets. If we have a set A intersect B, this is defined as defined as the collection of X such that X is in A and the same X is in what? B. Okay, so this is just a definition of intersection, but nevertheless we are going to use this in doing some using it to at least to simplify the proof. Now we have here that T1 and T2, tau 1 and tau 2 are the topologies on X. Now we want to show that their intersection is also a topology. Now for us to do this, we have to show that it satisfies the three axioms of topology. I want to show that the first axiom is to show that the empty set is in the topology and the whole set is also in the what? In the topology. Now when I say, since, as for the first one, since T1 and T2 are topologies on X, then it means that the empty set and the whole set are in what? Are in T1, and also the empty set and the whole set are in what? T2. Okay, you show that the empty set and the whole set are in T1 and the empty set and the whole set are in T2. So if the empty set is in what? T1 and also in what? And at the same time in what? T2, what does this imply? This implies that the empty set is in what? T1 intersect what? T2. We're using just our definition. Now since the empty set is in T1 and at the same time the empty set is also in T2, what does this mean? The empty set is also in their what? Their intersection. Okay, the same thing applies to the whole set. Since the whole set is in what? T1 and the whole set is in what? T2, then this means that the whole set is in what? Their intersection. So we have shown that the empty set and the whole set are in what? The intersection. Okay, now we want to show that the arbitrary union, union of sets, open sets in the topology is also in the topology. So take any collection of sets, take any collection of what? Open sets, that is the collection of O alpha such that alpha is in delta, where our O alpha is in this intersection of topologies. Remember, what we are trying to show you is show that their union is in this. Since if O alpha is in this, we want to show that their union is in this. Now we have that where O alpha is in this, for every alpha in delta. Now since O alpha is in their intersection, it means that O alpha is in T1 and O alpha is in what? T2. From definition of intersection, when O alpha is in their intersection, it means that O alpha is in this and O alpha is also in this. Now what this implies is that remember your intersection this thing, whenever you have an element in a set, is in this one and also in the other one. Now recall that T1 and T2 are topologies, And since they are topologies, it means that the arbitrary union of O alpha is in their topologies, abi? Arbitrary union of this is in their topologies. So since the arbitrary union of this O alpha is in this topology, since these two are topologies, then this implies that since O alpha is in T1 and O alpha is also in T2, this implies that their union also is in T1 and their union also is in T2, since these two are what? Topologies. Now, the union of this is in this and the union of this in this. What does this imply? This implies that their union, that the arbitrary union of O alpha is also in their what? Their intersection. Is also in their intersection. Okay, because the arbitrary union is in T1 and also the same arbitrary union is also in T2. What does this imply? It's also in the intersection. That's why I did a quick revision on sets, on intersection of sets, so that you have an idea of the definition of intersection of sets. Now we'll also take the similar approach to the finite intersection of open sets in the topology. So we now say take any finite OI such that I equal to n, where OI is in the topology is in T1 intersect T2. Now we know that since OI is in T1 intersect T2, this implies that OI is in T1 and the same OI is in what? T2. Since OI is in their intersection, then OI is in the T1 and OI is in T2. Now, if OI is in T1 and OI is also in T2, what does this mean? Remember, T1 and T2 are what? T1 and T2 are topologies. And if they are topology, it means that their finite intersection of OI is also in what? T1. And their finite intersection of this OI 1 to n is also in what? T2. Now this means that if their finite intersection is in T1 and their finite intersection is in T2, remember that if this is in this and this is in this, what does this imply? This also implies that the finite intersection of OI is in I equal to 1 to n is in T1 intersect T2. Okay, so this is what it means, that their finite intersection is in this. So therefore we have shown that the finite intersection of this OI is in this. Hence T1 intersect T2 is a what? A topology. The topology on what? On X. That's the end of the proof. Please do not forget to subscribe to this YouTube channel, and please, if you don't remember, try and rewatch the video again so that you will get more understanding. I just did it to simplify it in such a way that you will understand it. Thank you very much.